All right, so we look up the properties of our 18 by 71. I should have that tabbed, but what that do. So there's two tables in the back. Be careful with that. One's a metric table, one's a US table. So 486 is the selected W shapes, dimensions and properties. So 486 is the US version because it's in W, 12 by whatever. And then the metric one is the next page, 488, and it's millimeters and kilograms per meter. So ours is inches and pounds on these callouts. So we are an 18, W18 by 71. If I can find it here. Looks like it's on page 486. Oh, focus. $18.71 right there. Okay. Gives me the area, 20.9 in inches squared. We'll need that. Anytime you see a W shape, you can go get properties. You don't have to calculate things. So area is 20.9 inches squared. I'm just writing it down on the side. D, this D dimension is what they call the depth of the beam. You'll probably think it should be height, but it's the same thing. They just call it depth. And that's from here to here, top to bottom. And we'll need that typically. So what's our depth? It's going to be near 18, 18.5. So our D dimension is 18.5 inches. Sometimes you'll need like this base flange dimension. Sometimes you'll need that. If they cap this W shape with a plate on the side, then you'll need to know how far that plate is from the center line. So sometimes you'll need that dimension. Sometimes you'll need the thickness of this web. So this is called T sub W, thickness of web. And then there's thickness of the flange, T sub F. All of that's in here, right? So you can get all those properties as you need them of any W shape that's called out. Then next term, you're going to need things like inertia. We actually can look it up, which is a big bonus. We don't have to calculate it because once you go through inertia with me, you'll be like, this sucks, because inertia does suck. Lots of opportunity to screw it up. So if you can use a W shape for design, it's a lot easier because you can look things up. If you get all tricky and you take an L shape and you stick it on a C shape and then you put a plate on it, you just have made yourself a problem because you have to calculate the inertia of that stuff and it's a pain. Anyway, so when you're given this, you have a lot of properties you can pull. Section modulus, radius of gyration, polar moment of inertia, all of these things we'll learn next term and how we're going to use them. All of this is generated off of the area. None of this refers to structural steel. Okay, so the cross-sectional area of any structural thing is super important. And it doesn't matter what it's made out of. This could be made out of silly putty, right? All these numbers are still valid because it's based on that cross-sectional area. So that's kind of a trick. All right, I think we only need area and that depth. We'll go get it if we need something else. But I'm going to number them. I'll call that 1. I'll call this 2. W shape is 2. So my area of my second shape is 20.9 inches squared. My overall depth, which I'm just going to put down as a dimension, is like from here to here. And that is 18.5, and I know that's a half inch, okay? If we assume the plate's put on symmetrically, then we don't really care about this y-axis. We know it's like straight on down through the center, right? I can see symmetry here. Agreed? Yeah. So we don't need to calculate an X bar. We know it's right directly in the center. What we need is a Y bar. Everyone get that? Because that plate has thrown it off. Without the plate, if there was no plate, what's Y bar? Yeah, half of the 18.5, right? I don't have to calculate anything if I just use that shape. It's symmetrical. That's not always the case. Like an L shape, not so symmetrical. Like, I got to look that one up. But it's back there in the back of the book, so that's nice. All right. So then we can just apply this Y bar equation, which is summing the areas times the Y's over the total area. Okay. You all see this thing? What is this thing? Oh, some kind of advertising. There we go. So what's, oh, this is my number one shape. What's the area of number one? $12 inches times a half inch, right? And then what's my Y distance to that? It's going to be 18.5, whoops, dang it, plus half of the half, right? It's that distance right to there. So plus 0.25 inches. So A1, Y1. Everyone see that? Y1 would go all the way up to right there. $18. So it's this full distance. It's the distance of the W shape plus half the distance of this rectangle. So it would be a 1/4 inch up, not a half inch. So it should be 18.5, that number, plus half of the height of this plate. 18.5 plus 2.5. Now I need to add to it my area of my second shape, which is 20.9 inches squared. So that is the area. I don't have to calculate it, but I need to multiply by the Y distance to the center of that area, right? So that's going to be the 18.5 divided by 2. I don't know how I run out of space. And then all of that over the total area, which this area looks to be 6 inches squared for the plate, and then 20.9 inches squared for the W shape. I get 11.37. That makes sense. Yeah, so if it was just the W shape, we would be what, 9 1/4? Yeah, so adding the plate shifts it up, that makes sense, to 11.37. So it just gets kind of, it gets complicated when you add shapes together. Like we do, we'll stick a C shape will stick on top of a W shape. So if I calculate that the W shape that I'm working with, 1871, is not strong enough, I can make it stronger by adding a shape to it, capping it with a C shape that maybe is hanging over. So yeah. No, Y bar is where? Yeah, exactly. You're asking. I'll put it on. So halfway up this thing is about 9, so it's up in here somewhere, right? And so it comes from the bottom because everything does, and that's Y bar. So Y1, Y2 is the Y distance to individual shapes. If there's 6 shapes, you got Y1, Y2, Y3, Y4, Y5, Y6, right? And then in the end, after you get done calculating, you have that composite Y bar. Yeah, that makes sense? Yep. So it's in here somewhere. And just think, kind of, if it's a simple shape, like you can look at these things and go, oh, that should shift it up. Like here's one. Right, these are metric. When you see big numbers like that, that's 530 millimeters, 530 millimeters. So this is a W shape where they capped it with another W shape on its side. So this gets a little complicated because when you look it up, this thing's on its side, but the table is not on its side. The table given to you would be the W shape in its strong position. Okay. So then, now it's flipped over. So the information you're going to use kind of as Y bar information is going to be given to you as X information in the back of the book. Because it's not going to give you the beam in 2 positions. It's only giving you the beam in 1 position. You got to figure out, oh, this beam flipped over, so I need to be thinking about the X distance, even though it's a Y distance here. So that gets a little weird. But what's it going to do here? Like the individual centroid of this 530 is right there. It's in the geometric center, right? So with this added to it, and this is a lot of mass up here, not just a plate. There's a lot of mass and a lot of flange, a lot of vertical activity. It's going to shift it way up here. So Y bar is going to end up way up here somewhere. It's not going to be past the beam. So if you come up with a Y bar of 2000, that's wrong. It's not going to be up here, right? It's going to be kind of between the 2 axes somewhere. So this one has an axis here that the back of the book is going to call that a Y-axis, but not on this problem because it's flipped over, right? And this one is here. The Y bar is going to be in between those somewhere. That makes sense? So you kind of you can estimate, unless it's really complicated, which I don't think. Oh, this is fairly complicated, right? This is some engineer that's gotten really tricky. Not a friend of mine, but actually, I don't know why you'd ever do that. Can't come up with a good design reason for doing that, but yeah, so Y bar for this one's in the middle, Y bar for this one's pretty close to the same spot, and Y bar for this one is also pretty close to the same spot. So the overall shift of this axis, not much. It might be not at all. Like, does this say it's symmetrically loaded? Oh no, it gives you a dimension. So it's going to be in here somewhere. Now, the X bar or the location of the Y, there's one here, there's one out here, and there's one over here. So again, it's going to be in between there somewhere, but I'm not sure where. Good? All right. Let's, oh God, did I turn that recording off? Nope.